So now, next example, Q2-41. So what are the difference in this example and before? So in this example, we have two objects attached together. So the upper is load and the lower is buoy. So the object is cylindrical buoy. So cylindrical buoy. So this is the cylindrical buoy, 2 meter diameter and 1.3 meter height, and given weight is 12 kilonewton. Float in salt water, so salt water of density 1020. So now if a load of 2 kilonewton is placed on its tops symmetrically, means at the center. So the problem asking to predict the hash, which is hash is the maximum height of the center of gravity from center of gravity of load. So means half of the height load above the bottom of buoy, from the buoy, okay, to remain in stable equilibrium. So you know it's not a buoyancy, it's about stability. So problems ask you to calculate the hash, but the object must to remain in stable equilibrium. So the problem give us the hint so that the YMC must be greater than YCG, because the object the problem mentioned stable here. So if stability, so we know we have to follow the procedure. We have 5 steps. Okay, step number 1, at this time, suppose all students manage to calculate for step 1. So step 1, what to do? First, apply the buoyancy principle to locate the position of the object. What position we want to calculate VD, we want to calculate hash. So draw free body diagram. So one liquid, so we only want FB upwards. So we have two objects, we have 2W, W buoy, W load. So do summation force in vertical direction, and we don't have to calculate W because the W given as 2 and 12 kilonewton. So just put the value inside the equations. So now remember step 1, we want to get VD and hash. So get the VD, so we get the volume displaced 1.4 kilonewton. And after we calculate the volume displaced, we must get this and this. Okay, so we know, so for these problems, the depth of immersion, we don't have the unknown for depth of immersions, so you can put any unknown here. So as I put Y. Okay, so after we get the volume displaced, so we know the volume displaced for the cylinder also equal to pi r squared times Y. So 1.4 equal to pi r squared Y. So we get the depth of immersion because I put Y as my depth of immersions. Okay, so step number 2, locate the CB. So remember CB is the centroid of the immer parts. So we already calculated Y from step 1. So YCB for cylinder is half of the depth of immersion. So Y 1/2Y, so equal to 0.223. Step number 3. So calculate the locate the CG, calculate YCG. Okay, for object more than one object, so we cannot simply calculate YCG as take the 1.3 divided by 2, because we have two objects. So if we have more than one object, we must use this ratio. So mean YCG that we want equal to W1 YCG total times 1 CG that we want to calculate equal to W1 plus YCG1 plus W2 YCG. If we have 3 objects together, so we must have W3 plus YCG3. Okay, so brings the Y total here, so we can say the YCG equal to load times YCG plus load times YCG divided by W total. So what is YCG buoy? Because for this example, we have buoy and we have load. Okay, remember YCG is from the center of gravity of the object. So this is the buoy. So center of the gravity means at half of 1.3. So this is CG boy. So this is CG boy. So means 1.3 divided by 2. So what is YCG load? From the center of gravity of the load to the bottom of the object. Not this is our load, but our object overall is here. So this is, so in this example, YCG load is equal to H. So put the value of YCG boy and YCG load in this equation. So we get YCG, either you want to remain as this figure, or you want to simplify by divide the 14,000 K. So we get YCG equal to 0.143 H plus 0.557. Okay, don't worry, because we didn't finish yet our steps. We still have 2 steps, so maybe we cannot solve H here, but we still have 2 steps. So step number 4, calculate MB. So MB equal to I divided by VD. So for this case, if we cut at the surface, the I is circle, so pi d4 over 64. So diameter is diameter at the surface, means the diameter of the boy. So pi d4 over 64, we get I. So VD we already calculated at step number 1. So put the figure in here, so we get the MB equal to 0.561. Okay, step number 1. Step number 1 is calculate YMC equal to YCB plus MB and compare. So calculate YMC. So we already have YCB in step number 2. We already have MB in step number 4. So we get YMC 0.791. So 2 remain, remember 2 remain stable. So we can say that YMC must be greater than YCG. So YMC 0.791 must be greater than 0.43 H plus 0.557. So we solve the problem. At the end, we get the H must be less than 1.636 meter. Means if we design the H is more than 1.636, then the object will be unstable. To remain the object stable, H must be less than 1.636 meter. Okay, easy. Remember, if stability, so do the 5 step. Even though you have unknown along your journey to settle the 5 step, at the end we will solve the problem in step number 5. Okay, thank you.